And let's go. Today we are going to be looking at another paper. So the paper I have here is the May-June 2023. This is mechanics on an AS level. We're looking at paper 4.2. I guess the goal for this paper is kind of to go as fast as possible. Obviously, I'm going to want to be explaining concepts as I go, but I'm going to try and do it just as quickly as possible. All right, let's start into the first question. So here we have a particle of mass 1.6 kgs is dropped from a height of 9 meters above horizontal ground. I should probably say I haven't done this paper before, just in case anything happens. But okay, anyway, 1.6 kgs, it is dropped from a height of 9 meters above the horizontal ground. The speed of the particle at the instant before hitting the ground, just as it hits, is 12 meters per second. Find the work done against air resistance. Okay, so this is an energy question. They're asking us to find work done. So that's a good tip that we are looking at energy. Whenever I look at energy, I double check 4 things. My potential energy, my kinetic energy, is there work done by a driving force or an applied force? And then is there work done by a frictional force? So I go through my checklist just so that I don't leave anything out while I'm doing this. Okay, so then I take a snapshot of my before and after. So before is when it's at the top, after when it's hit the bottom. Okay, is the potential energy changing in the scenario as it goes from, it's dropping from a certain height? Yes. The reason is because the vertical height is changing. So potential energy is changing. Is kinetic energy changing? Absolutely, because it is dropped from a height and then the speed at which it reaches the ground. So we'll say dropped. It's not like thrown down. So we can assume it's dropped from rest. So that's changing. Is there any driving force in this? No, there's not a driving force. There's not an engine or somebody pulling it down. Gravity is pulling it down, but we are accounting for that in our potential energy. So we don't need to look at work done by the driving force. Is there friction? In this case, yes. They want us to look at air friction. Okay, so those are my checklists. And so then I write up an equation of my energy before, as well as any work done by driving force, and that is equal to my energy afterwards, as well as any work done by the frictional force. So it's basically what's giving energy to the system and then what's taking energy from the system. That's how I see it in terms of the driving force and the frictional force. The before and after energy, so each scenario looks a bit different. So here I just take a snapshot. So my blue snapshot is before and my green one is after. Okay, so before I have got potential energy and I don't have any kinetic energy. I also don't have a driving force, so all I've got is potential energy, and then all of that energy is going to be changed into kinetic energy, as well as it has to overcome friction. Okay, so this is how I start. Then I just write my formulas for each of these. Okay, work done by a frictional force, that's what they want us to calculate, so I'm going to leave it as work done. So I know my mass is 1.6, gravity we're just going to use as 10, height is 9 meters, 1.6, I know that my velocity when it reaches the ground is 12, so that's 12 squared, and then basically I'm calculating my work done here. Okay, so this is an interesting question. The reason why I'd say it's interesting a little bit is normally mechanics doesn't even look at air resistance. So now they're looking at air resistance, and that might seem a little bit confusing. But if we just treat it like a frictional force, we can work out that our work done to overcome friction is 28.8 joules. Okay, so I first do my checklist, then I do my equation of before and after, and then I just plug in the values that I have. So I would say this is a relatively straightforward energy question. They can get quite a lot more complicated than that. Okay, question number 2. Two particles, A and B, of mass that and that respectively, lie on a smooth horizontal table. Okay, so I'm already seeing what I think is momentum. So it's important that it's smooth, it's horizontal. We've got A and B, so that's 3.2 kgs, 2.4 kgs. A moves towards B with the speed of V, and collides with B, which is moving towards A, okay, with the speed of 6. In the collision, the two particles come to rest. Find the value of V. Okay, so now the particles afterwards are at rest. All right, so my big notes for momentum is make sure that you choose a direction to be positive. And then you need to show what's going in the positive direction, what's going in the negative direction with positive and negative signs. Okay, then we're looking at conservation of momentum. Whenever I do conservation of momentum, I just look at two particles at a time, or one collision at a time. So in this case, there is only two particles for now. If there is a third particle, just do two at a time. All right. So my mass times my initial velocity plus my mass. And then here we need to have a negative initial velocity. And that's going to be equal to 0 because both of these particles are not moving afterwards. Okay, so 6 times 2.4 is 14.4. So my velocity is going to be 4.5 meters per second. Okay, so that's how much A was traveling towards B when the collision took place. Find the loss of kinetic energy of the system due to the collision. Okay, so now what we want to do when we're looking at loss of kinetic energy, once again, I think I'm going to use blue again. I'm going to use my initial kinetic energy and then my final kinetic energy. So I'm taking a before snapshot and an after snapshot. So kinetic energy before is equal to my kinetic energy of A plus my kinetic energy of B. Right, so you just add up the kinetic energies of the two particles. That is a half mv squared for my particle A and a half mv squared for my particle B. My particle A was 3.2 and it was traveling at a velocity of 4.5, so that's what we've calculated. This is 2.4 and that was going at 6 squared. Okay, what you need to also know is with energy is not a vector, so we can just look at magnitudes. We don't need to look at direction for this one. Okay, and I am getting here energy of 75.6 joules. Okay, and then if I look at my energy afterwards, in this case, I don't have any kinetic energy afterwards because my particles are not moving. So if I had so much before and nothing afterwards, therefore I have 75.6 joules are lost. Okay, that's my loss in kinetic energy. All right, now we can jump straight into our next one. So this looks like a forces and equilibrium equation, but I see that they've got an interesting concept going on down here. I haven't read the question yet, but when I see something like this, something squared plus something squared is equal to 1, it makes me think of sine squared theta plus cos squared theta is equal to 1. Okay, so I've just got that in the back of my mind. But let's actually read the question. So, coplanar forces of magnitude 13 Newton, 15 Newton, 33 Newton, and p Newton act at a point in the direction in the diagram. Tan alpha is 4/3. Okay, so we know what alpha is. The system is in equilibrium. Equilibrium means all my forces in the x cancel out, all my forces in the y cancel out. Okay, now they're telling me to show that this. Okay. Alright, so I'm not going to be thrown off by this interesting thing that I have to prove. I know that I'm busy with forces in equilibrium, and I know that the sum of my forces in the x is equal to 0, sum of my forces in the y is equal to 0. So I'm just going to start there. I do think my trig identity is going to come into play, so I'm probably going to have to at some point have cos theta equal to one of these and sine theta equal to one of these. That's how I think it's going to work out. Alright, so let's go. In Cambridge, you never know what you're going to get. So it's good to just practice a lot of past papers. Practice as many as you can. Okay. What else am I seeing here is that we don't know the value of theta. Okay, so that might also come into play in terms of solving theta. Okay, so let's just start. The sum of my forces in the x direction are equal to 0. So I have got 15 cos alpha plus 33 cos alpha minus 30 cos theta minus p cos theta is equal to 0. Okay. I'm just going to quickly do a little sum on the side here so that I can work out what is my cos alpha. Okay, so if I get tan, the inverse of tan is 4 over 3 is 53.13 degrees. Okay, now I'm going to just keep that in my calculator, and then I'm going to say cos of my answer. That gives me a value of 3 over 5. Okay, what's actually happening here is if you draw a triangle, so if I've got my x and y axis, and I've got my alpha over here, cos is opposite over adjacent, and so in my triangle, my hypotenuse, I can calculate using Pythagoras, it's going to be 5, and then if I was to look at that, my cos ratio is 3 over 5, and I can also see that my sine ratio is going to be 4 over 5. Okay, so if they give you an angle like this, it's good to just use the exact angle. It's actually preferable not to go into decimals. Okay. Right. So let's keep going. I know my cos of alpha is 3 over 5, so I'm going to say 15 times 3 over 5 minus 30 cos theta minus p cos theta is equal to 0. And so I'm just plugging all of that in. I get 144 over 5 minus 30 cos theta minus p cos theta is equal to 0. Okay, can you see that I can make cos theta the subject of the formula? So I think I'm going to do that. I'm going to take my cos thetas to the other side. So I've got 30 cos theta plus p cos theta. I said I'm taking them to the other side, so they become positive. And then I'm left with 144.5. So I didn't really take the other side. I pretended not to go to the other side. Now I'm going to factor out the cos theta. And then I'm going to say cos theta is equal to 144 over 5 divided by 30 plus p. Which is another way of saying 144 over 5 times 30 plus p. Okay, that is looking similar to my green value here. Not quite, but similar. Okay, let's just keep going. If I now look at my sum of my forces in my y direction, they should also be equal to 0. So here I have 30 sine theta minus p sine theta is equal to 15 sine alpha minus 33 sine alpha, and that's all equal to 0. Okay, so please note, I don't have all the answers. Okay, I don't know where this is going to. I'm just sticking to my principles and hoping for the best here. So just keep going. Just keep going. Sometimes we can't see it immediately. Okay, so sine of alpha is 4 over 5. So that's 30 times 4 over 5. Oh, that should have said 15 plus 15. Okay. So plus 15. Oh dear, okay. I need to, these are not, so sine thetas. Okay, so 30 sine theta minus p sine theta plus 15. And then we said it is sine theta is 4 over 5 minus 33 times 4 over 5 is equal to 0. Okay, so I'm going to take out a sine theta over here. And I'm going to take my other number to the other side. So I'm going to do 33 times 4 over 5. And then I'm going to subtract 15 times 4 over 5. Okay, so my sine theta is 72 over 5 divided by 30 minus p. Okay, this is the same as 14.4 over 30 minus p if you just go to the decimal. And this one over here, if I say 144 divided by 5, that is actually the same as 28.8. Okay. All right, so initially I didn't see it because I didn't have my decimals, I had fractions. Okay, but I do know that I've done my working out correctly. I hope so. Okay. So what is going on? Luckily, I did make it a decimal, and now it seems to work. So I've got my 28.8 over 30 plus p. Let me rather make that blue, because I've already highlighted that. So that's my cos theta. And then the other one is 14.4 and 30 minus p. Okay, so I've proved the one is cos theta and the other one is sine theta, and I know my trig identity is that. So I think the way that I would write this in an exam is I would just start off with my identity. So I would say sine squared theta plus cos squared theta is equal to 1. And so I would say 14.4 30 minus p squared plus 28.8 over 30 plus p squared is equal to 1. Okay, not a straightforward question. This is definitely giving you some curveballs, but stick to your principles. You know equilibrium, you know free body diagrams, you know the sum of forces equals 0. Just start going for it. Okay, you can get quite a lot of method marks if you just stick to the principles. Okay, verify that p is equal to 6 satisfies this equation and find the value of theta. Okay, they've asked this in an interesting way. They're saying verify that 6 is a solution. So the way that I understand that is you can then plug 6 into the solution and see if it works. If they say something like show that, then you absolutely can't use p is equal to 6. You have to prove that p is equal to 6. But in this case, they're saying verify. So I am just going to plug 6 into my equation, plus 28.8 over 30. It is good to know those keywords, okay, because if you get it wrong, they won't necessarily except if you're just subbing things in if they actually want you to prove it. Okay. So 14.4 over 30 minus 6 squared. Okay, I'm just going to say that's 9 over 25. I could probably, no, 28.8 divided by 36 squared. 16 over 25. Maybe I wouldn't say it's equal to 1. I would just pick the one side, and then I would say that's, maybe I would say 25 over 25, which is equal to 1. Therefore, E equals 6 satisfies. Okay, I'll probably just write something as short as that. Okay, find the value of theta. Okay, so we can go back to either our cos or our sine and just plug in our value over here. Okay, so I know that this is sine theta. So I'm just going to plug in 6. So 14.4 divided by 30 minus 6 is 3 over 5. And so my theta is going to then be my inverse sine. And that's going to give me a value of 36.8. Well, let's rather just say 0.9 degrees, because that would be rounding off to 1 decimal place. So in your mechanics exam, you need to round off degrees or angles to degrees to 1 decimal place. Okay, so this was a really interesting question. Definitely becoming creative in how they ask things. Okay, stick to your principles and just keep going. If you see here, so they did ask you to prove that equation. If you couldn't prove it, then you could still do part B. So always look for part B's of questions. Verify that it's 6. You can plug 6. They gave you the formula. Plug it in. You can find theta. So that's 2 marks that you can get, even if you didn't do the first part of the question. But in the first part of the question, start and collect method marks. Okay. Right, so let's jump into question number 4. So, an athlete with a mass of 84 kgs is running along a straight road. Okay, straight road, whenever I see the word straight, I'm thinking kinematics. I may use kinematics for this. Okay. Initially, the road is horizontal and he runs at a constant speed. Constant speed means I can use this formula. Otherwise, I'd never use it. I've got to suvat. Okay, it also means that whatever the force is going forwards is the same as the force going back. There's no resultant force. The athlete produces power. Okay, when I see the word power, I write down my 2 formulas. Work done divided by time, or the driving force times velocity. Find the resistive force which acts on the athlete. Okay, so whatever is going forwards has to be the opposite of what's going backwards. Okay. So I'm going to dive into my power equation. Power is driving force times velocity, because they've given us enough information here. They've given us 60 watts, so we can work out the driving force if he's running at a speed of 3 meters per second. 60 divided by 3, and that is a driving force of 20 newtons going forward. And if he's going at a constant speed, it obviously means frictional force is 20 newtons going backwards. Okay. Now, part B. The athlete then runs up. Okay, cool. So now he's going up a section of road, which is 150 meters, and it's inclined at 0.8 degrees. So the horizontal. The speed of the athlete at the start of the road is 3 meters per second. Let's just put his body back on him. Okay. 3 meters per second. He now produces a constant driving force of 24 newtons. Okay, so the previous one was 20. Now he's got to give it a bit more force. The total resistive force which acts on the athlete along the section of road has a constant magnitude of 13 newtons. Okay, so this is the resistance force. And now we need to add his weight as well. Whenever you find an incline, we need weight. His weight going down. And that's different from a resistive force, okay? So 13 newtons going down, but he's also got mg sine theta going down. Okay, use the energy method to find the speed of which the athlete at the end of the 150 meter section. Okay, so forget about the forces because we actually need to use the energy method. Right, so I'm glad we have another opportunity to practice this. So we've got EP, EK, work done by the driving force, and work done due to resistance. So I'm also going to highlight my sections in the beginning and at the end. Okay. So, is the potential energy changing? Yes, because he's going uphill. Is the kinetic energy changing? The speed of the athlete at the start is 3, and he now produces a constant driving force. Use the energy method to find the speed. Okay, so we've got to assume the speed is changing because they want us to find the speed. Okay. Is there work done by the athlete? Absolutely. He's putting in a lot of work. Are there frictional forces? Absolutely. Okay, so now we're going to write up our equation. In the beginning, does the athlete have potential energy? So I'm going to say he doesn't have potential energy in the beginning, at least not relative to the end. So I'm rather going to say at the end, he has potential energy. So we need to give this athlete energy to get up the hill. Okay, he does have kinetic energy in the beginning, and there's kinetic energy at the end. Okay, so we're starting and ending with kinetic energy. Then the athlete is working to get up the hill, so that's force times the distance, and energy is being taken from the athlete to overcome friction. Okay, so that's also force times distance, but this is your frictional force and this is your driving force. Okay, so we've got a half mv squared. I should have just said work done initially, but anyway, I jumped into the equation quite quickly. Half mv squared plus your frictional force times your distance and your frictional force must always be parallel. Okay, so we've got a half. The athlete has a mass of 84 kgs, and initially he's going at 3 meters per second. Okay, then he's got a driving force of 24 meters, and he's going 150 meters uphill. He's 84 meters, gravity is 10, height. Okay, so we got to work out this height. All right, so whenever you're looking at potential energy, you're looking at change in vertical height, not the length of the slope. But we can use trigonometry. So in my triangle, sine of 0.8 is my opposite, which is my h, over my hypotenuse, which is 150. Okay, so h is 150 times sine 0.8. So that is 150 times sine of 0.8. Okay, I'm running out of space here. Plus a half times his mass times the velocity squared. We don't know the final velocity. We do know he's got 13 newtons acting on him and 150. Okay, please note that when I'm using my pluses and minus signs for energy, I'm not saying now that the frictional force is negative, okay? Because we're not looking at direction of the forces. We're just looking at energy, and I put them on the right side of the equation if they have a positive sign. Okay, so just keep all the signs positive. In the very beginning, make sure you get the right thing on the right side of the equation. Okay. 3 squared. I'm just going to write down, so that's 378, and then 24 times 150. $1759.23 Okay, I don't know, so half of 84, I'm just going to do that. V squared, and then 13 times 150. So sometimes my students like to first calculate each of these things on the side somewhere, and then put it into one equation. So that makes sense, especially because otherwise the equation can be quite long. I personally like to just do it all in one, but 1950, and then subtract 1723, and then I'm dividing everything by 42, and then I need to make sure that I square root my answer to get my actual V. And I'm getting a V of 2.53 meters per second. All right. So I'm glad that we could practice another energy question. I personally feel like this works all the time, but it does take some practice to know what's going where. Okay. Let's jump right into question number 5. So, a particle has a mass. Okay, whenever I see this, let me just start there. It's an incline, so we already know that we're going to have our inclined plane. And this is a very steep plane. So I just need to make sure that I draw my diagram and get my angles in the right place. Okay. So I'm just making a note to be careful because here when it's so steep, sometimes it's a bit tricky. All right. A particle of mass 0.6 is placed on a rough plane. Okay, so it's going to be friction. It's inclined, so there's going to be mass. Let's put that in already. We know that's acting down. Okay, the particle is kept in equilibrium by a horizontal force. So I don't like my force written like that. I prefer it going out this way. So I'm just going to politely erase it on this side, and I've just made it a pulling force on the other side. Okay. You might want to just quickly jot down on the side, just put a little, just draw a different free body diagram on the side. Okay, so I'm making it a pulling force. There is weight going down. It's acting on the vertical plane. The coefficient of friction between the particle and plane is 0.4. Okay, so my 0.4. Okay, what am I noticing here? My P has a component in the X and Y direction, so it's going to affect my normal force. That's really important. Find the least possible value of P. Okay, so my question right now is I don't know which direction friction is acting. Is P going to make the particle want to move up, or is P going to make the particle want to move down? Okay, so they say I find the least possible value of P. So when I'm given a question like this, the first thing I do is try to imagine, okay, well, what if P is super small? It's a tiny little P. Then this particle is going to want to roll down. Okay, and then my friction must be acting up. And that's the case that they want us to look at. If I imagine my P being huge, like really a lot, it's got a component going up the hill, so it's going to want to pull the particle up and friction is going to act down. Okay, but I'm not going to look at that for now because they're saying find the least possible value of P. All right, and so I know my sum of my forces in the X direction is 0, and the sum of forces in the Y direction is 0 because they do say it's in equilibrium. So the other thing is you need to know that there's a range of forces that is going to keep this thing in equilibrium. So there's a bunch of forces that it can go through. Okay. Right, so I'm going to start, I normally like to start in the X direction, but I think I'm just going to go into the Y direction first. The other thing I'm going to do, if my weight is over there, my degrees is going to be over there, 35 degrees. And then I know that's 90. So I'm just trying to work out my angle of my P particle. So that's going to be 55, and that's also 30. Okay. Right, so I've got enough angles to figure stuff out now. Let's go to my forces, my Y direction. My normal R is going to be there. Okay, And it's going to, so my sum of my forces, I've got R. And then P has got a component in the negative y direction. So can you see this big blue? That thing can be split up like this. So it's got a component in the negative y direction. So I've got my R minus my P cos 55, and then also my weight component minus my 6 cos 35. That's going to be equal to 0. Okay, so my R is basically P cos 35 plus 6 cos 35. Okay, I'm going to leave it like that for now. Then I'm going to go into my X direction. So if I'm looking at X, I've got different things acting up and down the plane. So I'm going to take down the plane as positive. So I've got my mg sine theta is going down. I always like to make the direction of motion positive. So it wants to slip down. My frictional force will act opposite it. And then I've also got a component of P going up the hill. So P minus P cos 35. This one must be 55 on this side. Gosh. Okay, minus P cos 35. That's all the forces in the in the X direction. That's equal to 0. So this is 0.6 times 10 is 6 sine 35 minus my frictional force, which is mu times R. Okay, I know what my mu is. My mu is 0.4. So I've got 6 sine 35 minus 0.4 times, now I've got my R value. My R is P cos 55 plus 6 cos. Okay, so now I've only got P's. That's nice. I got rid of a variable. It's still looking kind of complicated. You can always go into your, just plug these things into your calculator and just get numbers instead of trig. But I'm going to keep it for now. I like to practice keeping all my decimals, basically. Okay, then we have minus 0.4 times 6. 25 minus P. Okay, now I'm going to keep all my terms with a P on my left-hand side, and I'm going to take all my terms that don't have a P onto my right-hand side. I'm actually going to do it the other way around because because my P values I want to be positive. Okay, so I'm going to say 0.455, and I'm also going to take out a P. That's equal to 6 sine 35 times 6 times cos 35. Whew. Okay, now I can take the whole of the one side divided by the whole of the other side. So 6 times sine 35, subtract 0.4 times 6 times cos 35, divided by 0.4 times cos 55 plus cos 35. Okay, right. So there's quite a lot of calculating here. If you need to take more steps, do. But I also encourage you to practice just going, doing as much as you can, as quick as you can. So just practice, going. Find the least possible value of P, and that is actually correct, which is nice and encouraging. Okay, let us jump into question 6. If we just orientate ourselves, I've got a 6. Okay, so 6 and 7 are left. Okay, immediately when I'm seeing this, I'm seeing kinematics, and I'm going to be needing, it's It's varying acceleration, which means I am going to be using integration and differentiation. Okay, a particle starts at rest. Okay, so my velocity at naught is equal to naught. It moves in a straight line, so I may use kinematics from point O. The time after leaving O, the particle has that velocity, and I see a lot of variables. Okay, we B and C are constants. P has a velocity of 8 when T is equal to 4. Okay, so the way that I've written these things, it's basically a point in time. So here, my velocity is 8 if my time is 4. My velocity is 0 if my time is 0. Okay, and then it has a velocity of 13 when my time, so velocity of 13.5 when my time is 9. Show that B is equal to 3 and C is equal to minus 1.5. Okay, so this is just plugging in values and doing simultaneous equations. I'm not going to use my 0 because if I plug 0 into this, I'm not going to have any key values. Okay, so velocity, or let's just say 8 is equal to, and now I'm plugging in 4b plus 4 to the power of 3 over 2, c. That's 4 to the power of 3 over 2, I think that's 8. 4 to the power of 3 over 2 is 8. Let's see. Okay, I can immediately just divide through by 4. So my b is 2 minus 2c. And then if I do another one, so maybe this information I probably should have written somewhere else because it's taken up quite a lot of space. So just don't make your papers too messy, but you can write information somewhere else. So long as it's not stuff you're wanting to be marked, okay? It's more like your thoughts. Okay, so here I'm plugging in 9, so I know that it's 13.5. See. Okay, so 13.5. Okay, so here what I'm doing, I'm basically square rooting 9, which is 3, and then I'm raising it to the power of 3, which is 27. Hope. Okay, I'm just going to divide everything by 9 because it looks convenient. So 13.5 divided by 9. That's 1.5. Okay, so now I can say 2, no, oh dear. B is 2 minus 2c. Yeah, 2 minus 2c. So 1.5 minus 2 is minus 0.5. Okay, and that is what they wanted me to prove, so we are good to go. And then if I plug in my B is going to be 2 minus 2 times minus 0.5. And that gives me 3. Okay, so ran out of space a little bit there, but we got the answer. Okay, so that's just plugging in simultaneous equations. It's not really testing our integration or differentiation or anything. Okay, in this one, find the acceleration of p when t is equal to 1. Okay, find the acceleration. So when we're given a velocity formula, you need to understand how we go from one to the other one. Okay, so acceleration is change in velocity over change in time. We're not working with constant acceleration, we're working with varying acceleration. So we need to differentiate. To go down, we differentiate. To go up, we integrate. Okay, so we've been given velocity. And once again here, if you weren't able to prove the stuff above, just use it. So 3t minus 0.5 t to the 3 over 2. Okay, so that's my velocity. They want to know, find the acceleration when time is 0. So if I want to go to acceleration, that is my change in velocity over change in time. So I need to differentiate. and that just becomes a half. Okay, and then when t is equal to 1, so I'm plugging in my t is equal to 1, and that is literally going to be 3 minus 3 over 4 times 1 to the power of a half. Okay, so 3 minus 3 over 4. Okay, I'm not even going to plug in the rest because we can see the answer. So that's 2.2. I'm not going to plug in the rest because it's 1 to the power of something. It's just 1. Okay, so that is my acceleration. All right, also a straightforward question. So the first one was 1 mark, then 2 marks. Now we've got a 5-mark question. Okay, let's see what it is. Find the positive value of t when p is at instantaneous rest. Okay, instantaneous rest, that's when my velocity is equal to 0. Find the distance of p from 0 at this instant. Okay, so first of all, let's figure out what time does this particle come to rest. So we're just taking our velocity time formula and making it equal to 0. Okay, to find when is this particle equal to 0. All right, so I'm going to take out a t, and over here I'm left with, what, half a t. Okay, when I multiply back in, I'm adding my exponent. So 1 plus a half is 1.5. So that's correct. So t is equal to 0, or 3 minus 0.5 t to the power of a half is equal to 0. Okay, so let's just solve this on this side. So 3 is equal to 0.5. So I'm doubling it. 6 is equal. And then I'm going to square it. So t is equal to 36. Okay, we only want, that value. Okay, it's a positive value. So we don't want t is equal to 0 and t is equal to 36. They said find the positive value. So we can say t is equal to 36 seconds only. It's good to say only because then they know that you've considered it's not 0 but 36. Okay. And find the distance of p at 0 at this instant. Okay, so we know that the particle is it's moving, and then it comes to rest again at 36 seconds. There's no other part in between 0 and 36. Otherwise, we would have picked it up in the maths. Okay. So find the distance. So now we're going to go back up our little thing over here. We wanted to get to distance. So I'm going to integrate my velocity time formula. Okay, so my velocity is this. I'm just going to copy it. And now I want to integrate. And while so basically I've got a curve, whatever that looks like. So it passes 0 at 0 and 36, and it's an unhappy quadratic. And I want the distance, which is the area under the graph. Okay, if you understand the velocity time graphs. Okay, so my distance, I'm going to just do a definite integral between 0 and 36. Because my area is going to give me my displacement. I can integrate immediately. 0.5 t, so 5 over 2 divided by 5 over 2. Okay, and I'm plugging in 36 and 0. I can see if I plug in 0, it's going to fall away. So I'm just going to plug in the 36. But you must check that that is true. Okay, and this should give me my answer. Okay, so 3 over 2 times 36 squared minus 0.5 and 36 to the power of 5 over 2 divided by 5 over 2, and that gives me a final answer of 388.8 meters. If I was looking at 3 significant figures, I might just write there sig figs, so 3 sig figs. Okay. Just so that they know that I know I use significant figures, but I do prefer to write down more and then round it off to less. Okay, well, round it off to 3. Okay, find the speed of P at the instant it returns to 0. Okay, so we don't know when is it returning to 0, but returns to 0 means your displacement is going to be 0. Okay, so we first have to figure out when is the displacement 0. So I've now got my displacement formula, sort of. I'm going to just go from here. I've got 3 over 2 t squared minus, and then I'm just going to simplify this a bit, 0.5 divided by 5 over 2. That gives me 1 over 5 t to the power 5 over 2 plus c. Okay, so if we were to do an indefinite integral, we would have to add the plus c, but I know that I started from the origin, so my c is actually going to be 0. Okay. Because, yeah, I started at 0 and now it's going to return to 0. So I need to work out 5 over 2, when does it return to 0? Okay. To solve this, what I normally do is I'll take out my smaller t value. So I've got a 2 and a 2.5, so I'm taking out 2. And I'm left just with a half. Because when I use my exponent laws going back in, I've got to add my exponent. So 2 plus a half is 2.5. Okay, so my t is equal to 0, or I've got 3 over 2 is equal to 1 over 5 t to the power of a half. Okay, so now I'm going to just put 3 over 2, and I'm basically going to say divided by 1 over 5. I should have just said times 5, but anyway. That's 15 over 2 is equal to t to the power of a half. And so now I need to square it if I want to get rid of my root. And so my t is 56.25 seconds. Okay, I've taken up a lot of space to do this. Let's just see, find the speed of p at the instant it returns to 0. Okay, so it returns at that time. And now we want to find the speed. So I can go into my velocity formula and plug in my value. So my velocity, once again, is here. Okay, and I am going to plug in my time of 56.25. And what does that give me? Okay, that gives me an answer of, it gives me a negative 42.2 meters per second. So therefore I'm going to say my speed is 42.2 meters per second. So we don't give direction if they ask for speed. They give velocity, we can do that. And it makes sense that it's negative, because if this particle is returning to 0, it means it's coming backwards, so that's why it's a negative value. Okay. All right, let's see if we can quickly do this last question. So I'm seeing connected particles, 4 marks, 5 marks, 4 marks. Okay, so this is quite a big portion of your paper. Definitely not worth leaving anything out, so let's go. It's never worth leaving anything else. Okay, just keep going. All right, 2 particles, P and Q, have mass of that and that respectively. They're connected by light string that pass over a smooth pulley. Particle P is on an incline at an angle of 30 degrees to the horizontal. Particle Q hangs below the pulley. 3 points, A, B, C, lie on the greatest slope. AB is 0.8 meters, which is given, and then BC is 1.2. Okay, now I'm imagining they're going to have smooth and rough portions here. Okay, particle P is released from rest. Okay, U is equal to 0 at that point. It's 2 kgs, the other one is 0.25, so P is probably going to be going down. It's released from rest, and it slides down the plane. Okay, it is going down. During the motion of P from A to C, Q does not reach the pulley. Okay, the part of the plane from A to B is rough. Okay, this is what I expected. And it's got a coefficient, mu is 0.3. Between the plane and B, the part of the Q here is smooth. Okay, got it. Smooth. Find the acceleration of P between A and B. Okay, so this is a connected particle question. What we do is we draw free body diagrams of each particle and we write up our equation with Newton's second law. Okay, that's the gist of it. Pretty much most of the time. Okay, so here we've just, if I zoom into Q, I've got my mass acting down, so M times G, and I've got my tension in the rope pulling up. Okay, so my sum of my forces is mass times acceleration, and I know that my mass is 2.5. My mass times my gravity is 2.5. It's going down. I'm taking my direction of motion to be positive, by the way. That's positive. So if I look at particle Q, up is positive. So minus 2.5 plus T is equal to 0.25 times acceleration. Oh, I shouldn't actually split these particles up. I should look at the system as a whole. But anyway. Okay, let's just keep going. So particle P has gravity pulling it down. It's got friction pulling it up, and there's tension in the rope. Okay, so minus tension, so down is positive in this case. Okay, minus tension, minus friction, plus mg sine theta is mass times acceleration. Okay, I'm setting these up mu times r. My mass is 2 kgs. So it's 20 sine 30, and that's 2a. Okay, I'm busy seeing that I probably should have just worked with the system of particles. So if we look at the system, that means we can eliminate T, because they're going to be working against each other. So this is, we've got mg going down, we've got friction going up, and we've got mg sine theta acting down. Okay, and this direction is positive. So I know I've got minus my 2.5 of particle P, minus my friction, which is mu times r, plus my mg sine theta, or I could actually fill that in already, plus my 20 sine 30, and then my total mass is 2.25, so that's of both particles, divided by A. Okay, so I'm quickly going to zoom into R. Okay, so R, let me just draw it up here. So R is the only force acting in the y direction. If I look at particle P, the only force acting in y direction is the weight component, and acting against it is R. Okay, so my coefficient of friction is 0.3. My R value is going to be 20 cos 30. Okay, so let's see what we get here. So minus 2.5 minus 0.3 times 20 times cos of 30 plus 20 times sine 30, and then divided by 2.25. That gives you an answer of 1.02 meters per second squared. Okay, and that is the correct answer. So I probably didn't have to do those two equations initially, just the third one. Okay. Hence, find the speed of P at C. Okay, so now it's only traveling between A and B at that specific acceleration. A and B are 0.8 meters apart from each other. So it's going at that acceleration while they are connected. So my initial velocity is 0. My final velocity at B, we don't know, but that's what I'm going to work out. My acceleration is 1.02 and my distance is 0.8. So I'm just going to go v squared is u squared plus 2as. Okay, I'm going to work that out. I'm just going to leave all my decimals in here for my acceleration. And I'm getting velocity is 1.28 meters per second. So that's my velocity at B, not yet at C. Okay. Now my acceleration is going to change because it's not rough anymore. It's now smooth. So I'm going to draw up a new free body diagram where I've got my mg of my one particle, and now I don't have friction acting back anymore. So that's what changed. But I still have my mg sine theta. So if I write up an equation, I've got my negative mg of my one particle. So I'm just going to copy minus 2.5 of the one particle. And then I've got plus my 20 sine 30 of the other one is 2.25a. So I've got a new acceleration now because it's no longer rough. Okay, so minus 2.5 plus 20 times sine 30 divided by 2.25. So my acceleration is now going to be 3.33. Okay, and so we are going, our velocity is 1.28 to start with. We're trying to find our end velocity. Our distance in this case is 1.2 meters. And my acceleration is 3.33 meters per second squared. Okay, so v squared is u squared plus 2as. 3.3 and 1.2. Okay, so what is that? Plus 1.28 squared. And then I must make sure to root it all. So my final velocity at that point is 3.10 meters per second squared. I'm putting in the 0 because that would be 3 significant figures. Okay. And our last question for 4 marks. Find the time taken for P to travel from A to C. Okay, that's not too difficult. So I'm just gonna jump into my two Suvat equations. I've already got my information for both of them. So the only thing that I'm going to change is that I'm not looking now for final velocity, I'm looking for time. Okay, so I might just use my nice v is equal to u plus at. I'm going to be going with, okay, I suppose I wouldn't actually do this. Acceleration 1.02 times time. So I generally like to go back to information that I have. So I probably should have used a different equation, but anyway. 1.28 divided by 1.02, that gives me a time of 1.25 seconds. And then the other one Okay. Because here we're rounding off a lot of stuff. So my t is 0.546 seconds. If I add the two together, I'm getting something like 1.796 seconds. So if I was to go to 3 significant figures, it would be 80 seconds. All right, and that is the end of this. I hope that they can help you. I think my encouragement is no matter what kind of questions they throw at you, stick to your principles and just start going. And then generally it will sort itself out, but you can get a lot of method marks just from sticking to your principles and don't leave anything blank. That's a sure way to get nothing for that question. So just write down your equations, figure out what topic you're in, and don't stop. Okay, cool, well done.